Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today we are going to talk about the solubility of ionic compounds of group number 1 and the group number 2 elements of the periodic table. So let's start with the group number 1. I'm writing group number 1. The group number 1 is lithium, sodium, potassium, rubidium, cesium and the francium. The group number 1 has an oxidation state of +1. So it's Na positive, K positive, Rb positive, Cs positive and the francium positive. Now the elements of group number 1 are all metals. Now as they are metal, so the solubility will depend upon the ionic character, or we can say the charge densities. Solubility also depends on the ionic character, or we can say the charge densities. As we all know, down the group the radius of cation increase and has a charge density decrease. I'm writing down the group charge density, the phi, the charge density decrease and hence ionic character decrease, due to which solubility also decrease, due to which solubility also decrease. But there are some exceptional cases for the group number 2 metals. So let me write the group number 2. We are having a lot of exception, but in case of only group number 2 metals, I'm writing group 2 elements. Now the group number 2 is beryllium, magnesium, calcium, strontium, barium, radium. Now I'm excluding beryllium over here because most of the compounds of beryllium are covalent in nature. Now let me talk about the case number 1. Case number 1. When common anion is small, the group number 2 are all metals, that is they are all having the positive charges, that is Mg2 positive, Ca2 positive, Sr2 positive, barium 2 positive and radium 2 positive. Now when common anion is small, let me take an example of small anions. The examples are like F negative or oxygen 2 negative or OH negative, or we can say Cl negative, etc. The size of these anions are actually very small comparatively the metals of the group number 2. So let me form the compounds with the group number 2. For fluorine, let me take an example of fluorine, fluorides. I'm taking the example of fluorides. So the group becomes MgF2, CaF2, SrF2, BaF2, barium fluoride, then finally radium fluoride. Being radioactive, let us remove the radium from this list also. I have removed the beryllium and the radium from this list. Beryllium compounds are mostly covalent, whereas of that of radium are radioactive. So we will just discuss about for magnesium, calcium, strontium, and the barium. Now, here the common anion is small. That means the radius of cation is much greater than the radius of the anion. Now let's talk about the simple formula of the hydration energy and the lattice energy. For lattice energy, I have told you lattice energy is inversely proportional to the sum of radius of cation plus radius of anion. Now, as the radius of anion is very less than radius of cation, that means the sum of radius of cation plus radius of anion will somehow equal to the only radius of cation. Now, that means in this case lattice energy will only be inversely proportional to the radius of cation only. It will not depend upon the radius of anion. Now, as we all know, when we move down the group, the radius of cation will increase, due to which lattice energy will decrease. Now let's come to the hydration energy. In the previous lecture, I have told you, if we are looking for the solubility of any ionic compound, if we are looking for the solubility of any ionic compound, we will look for the both hydration energy and the lattice energy. Now, in case of comparison of the different compounds of the group number 2 elements, I am taking both the energies, that's lattice energy and the hydration energy. Now, what's the general formula of the hydration energy? Hydration energy is inversely proportional to the radius of cation, then separately inversely proportional to the radius of anion. Now, here radius of cation is very large. Radius of cation is very large, due to which 1 by r positive will get ignored. We will get the very less value of 1 by r positive, being denominator to be very large, that's radius of cation. That means our hydration energy will depend only on the radius of anion by the inverse proportionality. So hydration energy will be inversely proportional to the radius of anion. Now, in this case, we are having anion to be same for all the compounds, that's magnesium fluoride, MgF2, CaF2, SrF2, BaF2. In all the 4 cases, we are having anion to be fluorine. So in this case, R negative is constant, because we are all having fluoride ions in the magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride. So the radius of F negative will remain same. That means radius of an ion is constant, due to which in this case hydration energy will be constant. So being constant value of hydration energy, the solubility will not depend on the hydration energy in this case. So we look only for the lattice energy. We have just done that. Lattice energy is inversely proportional to the radius of cation over here. Now down the group, radius of cation increase, so lattice energy will decrease. So that means MgF2 has maximum lattice energy and barium fluoride has minimum lattice energy. That means the lattice of magnesium fluoride is very strong lattice, because lattice energy is very high. So it's a strong lattice, so strong lattice will always be less soluble. less soluble. Now, let's talk about the barium fluoride. It has a minimum lattice energy, which signifies that the lattice of barium fluoride will be very weak. It's a weak lattice. Being a weak lattice, it has more solubility. It will be more soluble. So that's the case number 1, when common anion is small. And I have given you the example of the small anions, that F negative, O negative, OH negative, Cl negative, etc. In case of small anions, the hydration energy is constant down the group, but lattice energy will decrease down the group. So we will talk about the solubility by relating it to the lattice energy. Now let's talk about the case number 2, when common anion is large. Case 2, when common anion is large. Let me take an example like SO4 2 negative. This anion is actually the assembly of 5 atoms, the 1 of sulfur and 4 of oxygen. Let me take another example, PO4 3 negative. This anion is also the combination of 5 atoms, 1 is of phosphorus and 4 is of oxygen. Let's take another example, NO3 negative. This anion is also the assembly of 4 atoms, the 1 of nitrogen and 3 of oxygen. So these anions are actually very large, due to which the radius of anion will be this time much greater than the radius of cation. Now let me take an example of the group number 2 elements. Let me take example in sulfates. That I'm taking magnesium sulfate, calcium sulfate, strontium sulfate, and the barium sulfate. Now I have already mentioned that radius of anion is greater than the radius of cation, due to which the sum of radius of anion plus radius of cation will almost be equal to only radius of anion. Now let's talk about the lattice energy first. I'm talking about the lattice energy. Now lattice energy is inversely proportional to the sum of the radius of cation and the radius of anion. Now in this case, the sum of radius of cation and anion is somewhat equal to the radius of anion only. Now in this case, we are having common anion to be sulfate. So in magnesium sulfate, calcium sulfate, strontium sulfate, barium sulfate, the radius of anion will be equal. So that means here the radius of anion is constant for this case. Radius of anion is constant. That means for this case now, lattice energy will be the constant. In the previous case, hydration energy was constant. Now let's talk about the hydration energy for this part. Now hydration energy is inversely proportional to the radius of cation plus radius of anion. Now in this case, radius of anion is very large. Now denominator is very large. That means 1 by R negative will be ignored. For getting the very small value, we will ignore the 1 by R negative, because R negative value is very large, so we will get the very less value of 1 by R negative. So that means here hydration energy will be inversely proportional to the radius of cation this time. Now as we move down the group, radius of cation will increase, due to which hydration energy will decrease. Now the lattice energy is constant for the second case, but hydration energy is decreasing down the group. That means magnesium sulfate has maximum hydration energy and barium sulfate has minimum hydration energy. Now, magnesium sulfate being having the maximum hydration energy will have maximum solubility. On the another hand, barium sulfate for having minimum hydration energy will have minimum solubility. So that's it. So these two cases are vice versa of each other. In case of magnesium fluoride, it is the least soluble, but in case of magnesium sulfate, it's maximum soluble. On the another hand, in the first case, barium fluoride being having the minimum lattice energy is more soluble, but on the another hand, barium sulfate for having minimum hydration energy will be the minimum soluble. So that's all for today. I hope you got today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.